Hi, Doctor. I want to make sure I say your name right. Nguyen?
Wing,
Sorry, what was that?
wing.
Wing?
Yeah, that's okay.
Yeah. Or should I just call you Chi?
Yes, that
Okay.
would be fine, sir. Thank you.
Okay. Great. Welcome. Thank you so much.
Yeah, thank you for inviting me.
Yeah, I'm excited. It sounds like an amazing project. So we'll be recording this and then we're going to put it on our website. So we have all of it is recording now. I guess it started recording when I joined, since I'm the host. So, if you have other people you want to share this with, you'll have a link that you can share it. And the person MSS, that it's Seth Bailey, is that right? I feel like at this point I remember now. Yes, great. I'm gonna I want to make sure we record everyone who's here. Right, we'll wait a couple more minutes. Let's see if Lynn joins. Hi, Kimberly.
Hi there.
Oh, great. We have a former presenter here. Hi, Mary. Thanks for joining.
My pleasure. Oh, can you hear me?
Yeah, absolutely.
Oh, oh yeah. Okay. I'll mute myself. Okay.
Sure. Hopefully, Lynn will join us. But if not, we'll keep going. Lynn is the principal investigator for this project. Let me just. All right, there she is. And then,
I'm, I'm still trying to get this computer to work. So, but we're getting there.
great.
Hopefully, I'll be able to even turn on my video and have everything work, which has been true for a while. But we're going to give it a try. Hello.
We have Mary on, Mary Barsony.
Oh, cool.
Yeah, so former presenter, that's exciting too, and lots of interns, and which is great. Sam, can you put in the attendance? Thanks. I'm trying to look for it, and then as I'm trying to host this, and it's not. I can't keep. And MSS is Seth Bailey. Okay.
Okay.
MSS is really good about coming, comes all the time. And then every week, every month, I ask what their name is,
Who
and
are you?
it's Seth Bailey. Now I know. Hi. So, hi, all our interns as well. Welcome. We can wait a few minutes, but I was telling Chi that we record this, and a lot of people watch this later because for East Coast people, this is a little bit late. And maybe for West Coast people, it's right, it's a little too early. So all right. So I'm going to share my screen. We're already recording. Let me get to the presentation. And so I'm just going to do a few slides um, at first, Chi, and then you have a slide deck. Is that correct?
Yes.
And then you can share your screen. So I'm just going to start off with an introduction, and we usually do just a brief bit of executive function um, information. All right, I'm going to share. Here we go. So welcome everyone. Thanks so much for coming to our monthly N3 speaker series. I just wanted to let you know that our next meeting is going to be January 21st, probably. We have a few ideas for who might speak, and we will definitely, include you on the mailing list and let you know what that will be. We're going to quickly talk about procrastination. That was one of the, when we talked about executive function topics that you wanted to speak about. That is one of the top ones because I think we all struggle with that. We have our guest speaker, Dr. Chi Wing. Is that, I think I said that the way you wanted me to say it. From the
Yes.
Sphere X mission, which is really, really cool. Then we're going to get a little bit of feedback from the for the evaluators, and then we'll say goodbye. All right. So just very quickly, we're going to talk about procrastination and maybe some strategies to help with that. All right. Raise your hand or share in the chat if you've ever struggled with procrastination. I'm going to raise my hand right now. I just had a recent task that I really, really did not want to deal with. And I got through it. All right. Great. All right. Why do so many people struggle with procrastination? So you can say aloud or in the chat, like, how does it feel? What are some of the things that you feel when you're struggling with procrastination? I'm gonna look at here. Yeah, we're gonna get Ariana back. I swear we will. Yeah. Um, I'm looking at the chat. You feel overwhelmed? Yep. Yep. I just had a thing where I felt it was literally felt like a weight on my back. Yes, it's definitely more fun to do other things. You'll find anything else. Emptying the dishwasher feels more fun than doing the thing that you have to do. All right. Whoops, sorry. Now I have to move this chat. I'm going to close it for a sec. So keep in mind, procrastination isn't just being lazy, okay? We use it as a way of coping with challenging emotions and negative moods induced by certain tasks. All right. These include boredom, anxiety, insecurity, frustration, resentment, self-doubt, and other things. it's not just about time management, it's about emotion management. All right. So, in the case that I was experiencing, I felt very, very frustrated that I had to do something that I thought I had already done. So, does anyone else have any thoughts? If you want to unmute yourself or put in the chat, like what are some of the feelings that you have when you feel, I think we heard saw overwhelmed. What else? Any other feelings? Like you just want to be denial. Yeah, immobilized. Mm-hmm. Time could be better spent elsewhere. Denial, right? You don't have to do it. Yeah, very unmotivated.
Some people have their hands
Demotivated.
raised.
Oh,
Ollie, Maxwell, and Sasha.
do you want to speak up?
And from before, though, when you had everybody raise their
Oh,
hands.
yeah.
Oh, okay.
Okay. Yeah. Okay. That's okay. All right. I'm going to move this chat. All right. So this procrastination is a small reward, but it gives us a momentary break from our anxiety, but it leads to more negative emotion, and the cycle actually ends up increasing anxiety. So you procrastinate, you feel guilty, you panic, you make excuses, and then you procrastinate more. It's not a good cycle to be in. So, some of the ways we can get over procrastination. First of all, forgive yourself. Everybody does it. Don't dwell on what you should have done. Focus on what you can still do. Okay? Show compassion. The kinder you are to yourself, the fewer negative emotions you will want to avoid by procrastinating. And then reframe tasks by finding something positive about them. Remind yourself of a time when this type of task worked out well for you. Okay? So I had a writing task I had to do. I really didn't want to do it, but then I had to remind myself it's okay. And there have been times when I actually realized that when I had to rewrite something, I realized that I could actually do a better job, and that felt good. Obviously, minimize distractions. So having things that are really easily distracting, like your phone, like YouTube, like, hanging out with friends, like try to minimize those. Do you have any tools that can help you with minimizing distractions? What do you do? Tools, strategies? Does anyone have any things that they do themselves? Yeah, lock your phone, distraction for YouTube. Um, oh, interesting. All right, there's YouTube extensions that allow you to only watch videos for class and not on the side. That's great. Put your phone under a pillow.
Oh,
That's good.
that's good to know because
Yeah.
I wonder if they can actually do that, like in general, since I hate all that stuff.
Yeah. Yeah. No, that's true. Especially, if you use YouTube as to show your videos and then it shows all these other crazy videos that pop up. Full screen the page. Oh, that's interesting. So things aren't put, yeah. I mean, you can turn off all your email or text things and all of that. Yeah. Because anything will pull you away.
I have a strategy I used when I had to do some research, and everything at home was distracting. I mean, everything. So I basically drove to the public library for a couple of hours every single day, and there's absolutely nothing else I
Yep.
could possibly do.
Yep. When I was writing my dissertation, I went to a cafe so that I would just have to sit there and do nothing else. And I'd get a big pot of tea that would take a long time to drink. and just sit there for hours. All right, ad blockers. Yes, for sure. Should have ad blockers on all the time. All right. Thanks for everyone's comments. I'm gonna close that. And then set reasonable goals. This is really helpful. And I think, it's something we forget a lot. Proximal learning goals can prevent procrastination. So SMART goals, specific, measurable, achievable, relevant, time bound, on the path to the larger goal. All right. So you can say, like, I'm just writing one page. If I can just write one page, or I'm just finding one resource to look at, or things like that, and then you get on the path, and then sometimes it takes you away and you get absorbed with it and you can achieve more, or you don't, but you get that one thing done. Plan on making mistakes and how mistakes can help you learn. Mistakes do not equal failure, okay? And then but you do want to set challenging goals. So, because it is motivating to achieve them and it'll increase positive emotions. It's just like put these other goals on the way towards the more challenging goal. Don't limit what you can do. And I'm telling this to a bunch of people who just completed amazing internships, and presented. So I know you can achieve very challenging goals, not to mention, all the other scientists that we have here who have done pretty cool stuff. All right. So, without any further ado, we have Dr. Chi Nguyen, who is going to talk about the SphereX mission. And Chi, why don't you take over from here? And I'll go to your bio slide here.
Yeah, thank you very much. So thank you for the invitations. I have a PhD in astrophysics from the Rochester Institute of Technology, Western New York. Before that, I got my bachelor degree in astronomy from the University of Arizona. So very drastic change in the weather.
I was going to say, I saw that.
Yeah, and right now I'm currently a postdoc at Caltech, and I'm working on the SphereX mission, which is led by JPL, and involves a lot of scientists at Caltech, as well as other university all over the country and also like from Korea. So SphereX, in a nutshell, is a near-infrared instrument, and that's pretty much my background. I was working on near-infrared spaceborne instrument, and also experimental cosmology. So basically, we're trying to understand the universe by building experiments to collect the data, and then give the data to our theories friend, and they'll come up with some theories to explain what we see. So outside of my work, I enjoy biking, running, and do a lot of backpacking, hiking. And this photo I include here is just to show you, um, how scientists look like in like the actual lab. Like we spend a lot of time doing our work. I'll show you some photos. But we also love to have some fun like during the work, because when you spend hours working in the dark lab, you kind of want something to keep yourself going. So there's a whole story behind those LED light. I can talk about that later if we have time. Yeah, I guess so. Let me try sharing my screen. And I apologize that I don't have a camera on my laptop, which is mind blowing, but apparently my laptop, which is like a new laptop, it just doesn't come with a camera for some reason. Right. Okay. Yeah, so today I'll be talking about SphereX. And I just want to start by saying that this project involves a lot of people. So here's a photo of the team, the people in the maroon polo, SphereX team members. We also have some people wearing like blue polos, they are from the Punch experiment, which is another satellite that was launched together with SREX on the same Falcon 9 rocket, which is in the background, you can see there. So just to say that everything I'm going to show is the result of a lot of people working together as a huge team effort. So just want to acknowledge that. So here's the brief outline what I'll discuss. So I'll just give an overview of the missions and the science, and then I'll go over like some the timeline, show you some photos of some of the tests that we did on the satellite before we launch it, and then I'll show you some example of SREX data. I just want to say that the SREX data is available publicly, so all of the data that I'm showing you is available to everyone to use, and I'll show you the website where you can collect the data. All right, so what is SREX? So the mission is a mid-X mission. Was launched in March on a Falcon 9. So mid-X is a classification of NASA missions. It means that it has a cost cap of around $500 million. It has a principal investigator, Dr. Jeremy Bock at Caltech. So the payload itself was designed and managed by the NASA Jet Propulsion Lab, JPL. And what makes SREX really special is that it's the first full sky survey spanning an important infrared window with 102 spectral bands. So there have been some on-sky survey in this wavelength region in the past, like the 2-micron on-sky survey or 2MASS. But this survey tends to be at longer wavelength, and they tend to use like broadband filters. So the power of SREG is not that we won't just provide imaging data, but we also provide low resolution spectra for every 6.2 by 6.2 arcsecond on the sky. And that will greatly expand the science capability, because now you don't just see like the distribution of galaxies or like other stars in 2D, but you can also like figure out the distance to these objects. And the chosen spectral windows is such that it overlaps with the longer wavelength tail of the Hubble Space Telescope and the shorter wavelength ends of JWST. So that will allow like more synergies with other telescope. Like you can do further follow-up studies with JWST after you use like SREX data, for instance. The hardware, as well as the data analysis pipeline, are specifically designed to address the three science teams that I list here, and I'll go over them in a little bit more detail in a second. But in addition to this team, the data will also be available to all of you. So if anyone, we envision that there will be a lot more studies beyond what we have envisioned here. And that's one of the reasons we're very excited about. The satellite. So the first theme that I'm going to touch on is cosmology, where we try to understand the origin of the universe by studying the physics of inflations. And the second theme is understanding the formations and evolution of galaxies by studying their imprints on the extragalactic spectrolight. And the third theme is searching for ice and water in the Milky Way by measuring their emission and absorption features. Okay, so for the first one, which is cosmology. All right. So for the first science theme, this schematic here is the generally accepted standard model of cosmology. So the universe started with the Big Bang, and then inflations happens when the universe grows exponentially huge in a very short period of time. As you can see here, in 10 to the negative 32 seconds, the universe expanded extremely quickly, and ever since then, the universe has been expanding nonstop. And a lot of what we use to construct this model is based on observation of the cosmic microwave background, or CMB. We actually, scientists, like we kind of have the big picture of like how things happen and the order of like how the expansion happens. However, we actually don't know a lot of the details of inflations, like what really drives the inflations or how the initial conditions of the universe was actually is. So there are a lot of different theories. For example, here in this illustration, we have two family models to explain inflation. One is called the single field, and the other one is the multi-field theories. So these quantum field theories, they can on produce what we observed during the CMB, and the one that do not produce at the CMB, they have already been ruled out as like not realistic, because they cannot reproduce what we observe. Now, what we do know about cosmology and about inflation is that in the early universe, the primordial matter density fields are not uniform. They actually have small deviations that create cripples with slightly higher density than their surrounding. And when inflation happens, these cripples are amplified in spatial scale as well as in amplitude. And after that expansion, matter started falling into those denser regions because they have stronger gravitational pulls. And this is where stars and galaxies forms along these cripples. You may have heard this clustering of structure referred to as the cosmic web. So the CMB is a snapshot of this cosmic web. However, it's just one snapshot in like 400,000 years ago, and over time, as the universe is growing, as stars and galaxies are forming, and the cosmic web is growing, different theories will predict like different distribution of galaxies in 3D. However, we don't have that data yet. So one thing that SphereX is gonna do is to map out the locations in 3D of hundreds of millions of galaxies, as you can see in this volume here, and that will allow us to identify, to rule out, to decide like which family of inflation theories to actually explain how the inflation process happened. That's in a nutshell. Of course, there's a lot more details on like the math, like how we go from galaxy distribution to like quantum fluctuation theory. But that's like the details. The main takeaway for us is that we don't really have we don't have a large scale survey that can map out like so many galaxies in 3D yet, and this is where SREX gonna be really useful for. And the second science team is galaxies formations and galaxies evolutions. So as you can see in these figures, like the places where a lot of galaxy cluster, that's where like you have like really massive galaxy cluster. So those are very easy to, those are what galaxies, traditional galaxy survey usually detects. But in addition to those like massive region of matters, galaxies still form along like the fainter filament and even in like the less dense zone. So there is still matters there. There are still galaxies producing light. However, those galaxies tend to be it's very difficult to detect them, and sometimes they just fall below survey detection limits, even for like something like SphereX. So in addition, so the second science team, for the second science team, we do not try to probe all of these individual galaxies. That would be for the first science team, like we identify about 400 million galaxies. For the second team, what we measure is the total light productions from on galaxies. So we do not try to distinguish like the galaxies, like one galaxies from the other. We just measure on of the light production. And theory of galaxies evolutions have they can predict how many photons we should observe given the certain conditions throughout the history of the universe. And again, much like inflations, there's still a vast a lot of different theories, a wide parameter space on like how fast galaxies evolve over time, and each of them would arrive at a different prediction for the total photons emitted by one of the galaxies. And much like the galaxy distribution, we also don't have a very good data point or like what is the total light production on galaxies across the history of the universe in the near-infrared wavelength. And this is one of the data that SREX will produce. It will measure the total light productions on galaxies in the near-infrared window from our on-sky map. And the third science team is a lot closer to home, where since we already make like this map up, like pretty much we map out the whole skies in near-infrared wavelength. This also happens to be where we can find ices and water. And I'm using a broad definition of ice here. So we don't just look for H2O, like just water ice, but also other organic molecules that are important to life on Earth as we know it, like methanes, carbon monoxide, carbon dioxide, like the elements that you can see here on this plot, this inlet plot. So as we make the map of the whole sky in certain like planetary disks or young stellar system in the Milky Way, if they have like these molecules, they will tend to absorb the light signature. So we'll see like holes in our sky, in our on-sky maps, and that's when we know that in those like part of the sky, there may be molecules that are important to life. So we don't have like excellent spectral resolutions like JWST, but we have a broad coverage of the entire sky. So astronomers can look into our data, identify their favorite stellar system or their favorite gas cloud, and then do follow observations with JWST, and that will give them more better picture of like the dynamics in like those systems, for instance. Yeah, so that's another theme of our science. Now, as I mentioned multiple times, there are a lot of other science that can be done with our near-infrared data. So imagine here, this is an example of an on-sky map from a previous NASA missions. So we'll produce something like this, but we actually will produce 102 version of this. And at each wavelength, you can learn something a little different, and I'll actually show you some example later. So people can use our data to study galaxies, can study stars, they can even study quasar, black holes. Because we map everything in the sky. You can also look at comets, which we actually did, and I'll also touch on that later. And then something we never, I'm sure there will be other topics that we didn't think about that people can use our data for. And in the past, I usually say that, oh, someone will probably come up with something new. But now we actually have the case where someone come up with something that was not listed on this list. And I'll touch on that, which is actually very interesting. All right, so here's for the more fun part where we look at like hardware stuff. How does SREC actually look like? So this is the 3D models of SREC, the satellite. So we have the telescope, which is the black part structure here, and the telescope is surrounded by 3 photon shields. So these photon shields would help shield our experiment from straight light from the sun, the moon, and the earth. And then underneath the telescope, we have 3 layers thermal subsystem. So this thermal subsystem allow our instrument to cool passively. So there's no active cooling on SphereX. We are not limited by like the mission time, the mission lifetime is not limited by the coolant needed to keep our experiment going. So here's a cutout view of the telescope. It's a small telescope, it's only about like 20 centimeter, but it has a very wide field of view. So we decided to have a big field view, which allow us to actually like map the sky very quickly. So in just about 6 months, we can cover the whole sky. So it for people who are not familiar with like the concept like field view, the moon on the sky span about half a degree across, and our field view is 3.5 by 11 degrees, so it's massive. And the telescope is the whole like satellite has to be cooled down to less than 80 Kelvin because we are a near-infrared experiment, and at if the telescope is above 80 Kelvin, then it will actually emit a lot of thermal infrared, and we don't want something like that. We want the telescope to be cooler than that, so we do not emit lights that can contaminate our data. And the type of detector we use also work really well below 80 Kelvin. So here are some photos of the focal plane assembly. So we have the telescope here. You see those blue light denotes like the path of the light coming into the telescope. And there's a beam splitter that split the light into two focal planes based on their wavelength. And the reason we have to do it is because the type of detectors we use have a wavelength cutoff at 2.5. So the wavelength coverage of SPHEREC is from 0.75 to 5 microns. And we have 3 detectors covering 0.75 to 2.5, and then other 3 detectors that covering 2.5 to 5 micron wavelength. Sorry, this is supposed to say micron, not millimeter. So each focal plane, and here's an example of one on the lower right side here is photo of the 3 detectors. On top of these detectors, we put an assembly of linear variable filters. So the photo in the middle, without like the rainbow-looking things, that's the linear variable filters. These linear variable filters, what they do is they vary the spectral response along one direction. So in this photo, the spectral response varies from the top to the bottom. At each rows, there will be like different wavelength will be let through this filter. And what that means is for our detectors, each row pixels will be responsive to a different wavelength. And that allows, like whenever we take an image, we'll take data, we don't just image the sky, but we also have data at different wavelength. And have animations that illustrate like how we can, how we do that survey. So you can see here, the bottom of this greenish cone is SPHEREC, and the half moon shape is the zone that we can observe, like to avoid the sun and straight line from the sun and the moon and the earth. So we take an image and we use different, like a rainbow here to denote like the different wavelength that a detector, a row of pixels on our detector can see. So we'll take an image of the sky, we move a little, we steer the telescope a little bit, take another image, and then as the motion, like the spacecraft going around the Earth move, our zone of avoidance move with us. So we have to make a big steer and start taking data again. So as we do this coverage, like over and over 6 months, we'll eventually map out, like each of these color band, like you can focus on each of these color band on the rainbow, will cover the whole 360 degree celestial sphere. And that's actually the motivations behind the name Spherex. So you can see in the inlets here how we sort of cover the whole sky. And we actually pass over the north and south ecliptic pole multiple times a day. So in the north and south pole, we actually have better sensitivity than the rest of the sphere. And that is where we define like the deep field, where we can see like some tensor galaxies and can do slightly better like studies for very faint galaxies in boson. So anyway, that's the big picture, like the concept behind Spherex. The next part, which what I'm actually a lot more excited about, is like how we build this instrument. So here's a somewhat like a very busy slide, but don't have to like worry about like all of the details. Just want to give you on a big picture of like how a satellite mission comes together. So this is the timeline of Spherex proposal. So the concept started around like 2012, and we went through like multiple phase proposal to NASA. So initially, Spherex was envisioned as a small explorer mission, where the cost gap was about $150 million. They went through a study known as Phase A, where Caltech and JPL engineer put together model and explained to a panel of NASA experts, like this is our vision, this is how we're gonna build our instrument. But unfortunately, they were not selected. NASA picked a different missions called XP to study the black holes and X-ray. So that's what this new inlet is for. But the team did not give up on that process. They revised the proposal, make Spherex more ambitious. So now we propose for a mid-X mission where the cost cap is $400 million. So that's a lot more money, but it allows us to build a bigger satellite. We can take on a lot more risk, but also a lot more science. So that process took a couple years to upgrade the SMEX proposal into the MidX. And then Spherex was eventually selected in 2019. And you can see like this photo of like the proposal on my boss desk is basically like the size of a few dictionaries. So there's a lot of work that's just going on, like that just went into developing the design, the initial concept for the missions. And then from 2019, we started actually like fine-tuning the design of the missions, but then 2020 happens and there was shutdown due to the pandemic. So a lot of the work during that period is actually done like from home. Like here's some photos from our electrical engineer. Like he did a lot of the work from like his garage, developed like some prototype electronic parts at home in his little workstation. And back then, like the model of Spherex is still a little bit different. Like our photon shield is still like a deployable shield. But since then, we have like revised it, changed the shield a little bit, make it a different shape. We don't need to deploy it anymore. Just fly the mission as is. Just show you some how it changed over time. And then I chose Spherex during phase C, which is around like 2021. So this is when we actually finalize all of the design and we start like building small parts. We have to do testing at multiple level. Like we have the LVF. So this is the LVF just by itself before we actually assemble it, test it at that level, and then we put it into like the assembly of 3 LVFs by what I showed earlier. We do the testing again, make sure that when you go from one level to the other, like the the quality of our hardware, like all of the characterizations doesn't change. Like everything has to be consistent. And then we have some test chamber, like vacuum cold that reproduce the cold vacuum condition in space. So here's a photo of me and one of our lab assistant posing with like the vacuum chamber before we close it. So this is for the component level. So this is like the size of the focal plane assembly. And in the meantime, the telescope itself is being built and tested by our vendor at BA System in Colorado. So here's their photo of like, the optic testing they were doing at the time. And you can kind of see the scale of the sphere. Like this is the telescope itself, like compared to like a human. So it's not a very big telescope, but it can do really cool science. And then around like 2022, 2023 is when we start bringing the different systems together. So we have again, the focal plane assembly, the telescope, and then the thermal subsystem. That's the system that's at the bottom of the assembly. So you can see that we put them on together at Caltech. We don't have the photon shield because the photon shield is actually pretty huge for like our lab, and we don't need it for a lot of the lab testing that we did at Caltech. So we just have the telescope and the focal plane assembly and the thermal system as seen here. So now again, we bring everything together. We already characterize the system at a component level. We know how well everything works. Now we put them together. We have to test again because, like I said, we want to make sure that when we move from one level to the next level of the assembly, everything has stay consistent. For example, like I'm in charge of the detector to make sure that the detector noise is still consistent when we put it together with the telescope. And now so you remember what I said earlier, like we have like this like small like test chamber for the focal plane assembly. Now when we have bigger hardware, we need a bigger chamber. And this is actually contributions from our collaborators from South Korea. They design and build this chamber the size of a really huge like SUV, as you can see in this photo. They built it in Korea and then ship it to Caltech in Pasadena, and we bring it into our lab. Our building doesn't have a loading dock, so we actually have to open up the basement and just lower it into some crane like that. And this is the team from Korea coming over to show us like how to put the chamber together and how to put the telescope inside the chamber. So you can see the scale of the chambers relative to like the human again. So we have to put the whole telescope thermal subsystem inside. So some of the tests that we do with our CASI chamber is so just a few examples of some of the tests we do, because we also did a lot of tests. So a very important test for a telescope is focusing. So we have to make sure our telescope is in focus, especially since SPHEREC doesn't have a mechanism to change the focus once it's in orbit. So we have to launch it with the best focus. So the telescope is inside this chamber in this view. And then we have like external like optics that allow us to simulate a light source, to like simulate like stars in the lab. And then we'll see like how we take image of those test stars and see how well the telescope was performing, and then we make any adjustment if needed to make the image quality better. So you see the window here is actually a sapphire window. It's designed to filter out a lot of the thermal emission from the lab. So in this photo here, sapphire is not transparent to visible light. So like when we look at the window, like we actually, it's kind of like a mirror. You can see our reflection in it. That's why we take this photo. But for infrared wavelength, this window is transparent, so the infrared photon can actually pass through. And that's good because then we can filter out a wavelength that we don't need for our experiment. So here's an example. Like think about like when you go to the eye doctor and you do like they check how well your eyes focus, like they will show you like the letters thing, and then it show you different like lenses and say like which one would give you like the best lens. So what we did for Shrek is kind of similar like that. Here's a movie of what happened when we take image of the simulated star field. So there are like 5 stars here. And then as we adjust like the distance of those stars, we adjust like the setting of our simulated stars, we can see the image quality change. And the simulated star setup would actually tell us like how much we have to adjust the distance between our focal plane assembly and our telescope to get like the smallest star size. That's the best focus quality. And then we have to do this test like 3 times, because the first time is just to get like, do we need to adjust the focal plane assembly at all? So that's just the initial assessment. And then we make the corrections to get the best image quality. And then we bring the telescope and the whole telescope assembly to JPL, which is like what this photo is taken in JPL. We put this whole assembly on a shaking table that simulates the vibrations of a rocket launch. And after that vibration test, we bring the whole assembly back to Caltech, and we repeat the focus testing to see if there's any focus shift, because we want to make sure that our telescope is in focus and it stay in focus after we launch. So that's why I have to do it 3 times with a vibration test in the middle. And we did that, and we find that our design was very robust. The vibrations did not affect our focus quality at all. So that's a good thing. So we passed that test. And then another test is spectral response, which involves this test apparatus that look like something out of a sci-fi movie. So this is not the structure. The golden sphere is known as an integrating sphere. What it does is it just make you can put light into the sphere, and the light will bounce around. And once it exits the sphere, the light is very uniform. It means like there's like no polarizations in those lights. It just help us kind of like it help us remove some of the informations from the light and help us have a cleaner measurement. And the structure, the bucket cone looking thing is known as Winston cone. So it works together with the integrating sphere to produce like that light. So you see the output here, that's the side facing the telescope. So we just put like a small light source into the sphere, and that light source may carrying a lot, like it may not be entirely uniform. But once it exits the Winston cone in the sphere system, the light is very uniform. The reason we want that uniformness is because, as I mentioned earlier, because of the LVF, the linear variable filter, every row of our detectors is sensitive to a different wavelength. So when we use the Winston cone and a setup, a benchtop light setup, we could input light as a very specific wavelength into our telescope, into the Cassie chamber, and then our telescope can take an image of that light. And thanks to the LVF, as you can see in this movie, at different wavelength, only certain part of the detector would respond. That's the curved part. And our spectral response, it's not a perfect roll, but it actually has a little bit of a curvature to the linear variable filter. So the goal of this measurement is just to figure out like which pixel is sensitive to which wavelength. It's very simple goal, but it took us quite a long time to like do this measurement, because we have to step through like hundreds of wavelengths, and we have to do that for the whole window between 0.75 and 5 microns. So it took us about like a couple weeks running experiment nonstop. So at the same
Dr.
time,
Nguyen,
yes.
sorry, we just have to wrap up soon because we still have to do our survey.
Oh,
If
okay,
there's-
yeah, sorry. So I'll speed up then.
Thanks.
Yeah, so here's just some more photos. This is the photon shields. We put the telescope and the shields together. We send a payload to BA system in Colorado in February of 2024. Here's the whole thing put together. And they do more testing in their like vacuum chamber. This is mostly for the spacecraft, so no more instrument characterizations. Just want to check that the spacecraft is working as expected, and then we send it to Vandenberg Space Force Base to launch. So the launch was in March 2025, like earlier this year. So kudos to our teams because during the launch campaign, like we have the fire in LA, and many of our team's members were actually affected by the fire, but they still they managed to push through to keep on schedule. This photo, I'll skip this video, but it's available online if anyone ever want to like watch it. Basically, it was launched on a Falcon 9 rocket, and then after we launched, we spent a month in March and April to commission the project. So the commissioning happened at JPL, and then we took our first image, and this is the part where I said that we learned things that was surprising to us. So this band of light that you see here in the purple detector, so the colors is like fake colors to help people like understand the idea of like different pixel have different wavelength. So that is helium in the atmosphere. So apparently our emission, we see a lot of helium emissions in the atmosphere. And StreetX allow other scientists now to map out like the density of helium in our atmosphere, something we totally did not plan for. We see that everything is working nominally, like you see a lot of galaxies and stars in our data. Everything's in focus, which is great. And actually, we started our full sky survey since May, and we are at almost like full sky coverage. So this map was made by my collaborators a couple, I think like last month. So right now, like we already fill in a lot more gaps. So as you can see, we will produce 102 maps of the whole sky, and some of the artifact you see here is due to data like not being collected yet, but this should be filled in very soon. So here's another zoom in. So this is the whole galaxies, and you just zoom in to one part of the sky. Every dot on this image is galaxies or stars. And the reason you see like different colors here is due to like different wavelengths. So like some galaxies that are very young, very nearby, they appear very blue and green. And then there are some galaxies that are very red. Those are galaxies that are really far away, and you would not be able to see them unless you have like an infrared missions like StreetX or JWST. And yeah, we can also observe comets. So you may hear about the Three Eye Atlas comets from the news. It's believed to be an interstellar object. So we also have some observations of that. We have a paper out on it. So again, it's one of those signs that we did not expect to do, but we managed to get the data. Yeah, so I'll skip over this. Just want to say that all of this data is available to everyone. If you ever want to use our data, and just this is where you can get the data. We have the tools. So the data come with documentations. So you have the tools to help you use the data. You don't have to be like an instrument like scientists like me to understand it. So yeah, I'll leave this at my last slide, and thank you very much. And yeah, sorry for going over time.
Thank you so much.
We're
Yeah.
really excited at the
Amazing.
beautiful new data, and we look forward to seeing a lot more in the future.
Yes, and we actually so some of the data I could not show to you because we'll have like the
Right,
press release. We have a press release very soon with like a full sky image.
Are you going to be at the AAS meeting in Phoenix?
Yes. Well, I hope
Okay.
so. So yeah, we'll have a section at AAS, and we actually have our student who make those mosaic image that I was showing you. So they'll be there and talk about like how to get those maps.
Okay, cool.
Yeah.
Okay, well, I think we have just a few minutes now to do our little survey. But thank you so much. It's, really exciting mission. I'm looking forward to seeing more stuff at the AAS.
Yep, thank you. And feel free to like reach out to me if you have questions. If you use our data and if you find something interesting in the data, we'd love to hear about those.
And amazing images. It really helped for a non-astrophysicist to get some conception of what you're talking about. It was a beautiful slideshow. So
Thank you. Yeah, I wish I have so like yeah, it's very difficult for me to like try to explain all of this without being able to show you guys the full sky image, but it's coming on the news very soon.
Yeah.
So
Well, the
just look
one
out
that
for it.
you were showing where it was going around and taking the pictures, that really made it clear what it was actually doing.
Thank you.
All right, I'm going to share my screen briefly. We're going to allow Kim, who also has the same last name, so that's pretty cool, to do our evaluation. And I'm going to put up the questions in the evaluation.
Yes, thank you. Do you want me to
Okay.
read the evaluations or?
Oh, I can open up the screen.
Yeah.
And then we can put them in the chat. We can do one at a time. We have one at a time pop up.
Yeah, we have the slides, right? Don't we have these questions on the slides?
Yeah.
Yep.
they're
Can you
individualized.
see the slides? Yeah.
No.
Oh, you
There,
can?
yeah, you're not in slideshow mode, but anyway.
Oh, okay. Here we go.
There, that's better.
Yeah.
So just put, oops, I'm gonna go back. Kim, do you wanna?
Yeah, no problem. Yeah. So our first question is, what takeaways are you leaving this meeting with?
You can enter that in the chat.
Give you a few minutes to respond. And your responses are really great feedback for us as this project wraps up. We're still using it. We're still writing the summative evaluation report. So any feedback you can give us right now as we're writing the summative will be hopefully beneficial to continuing in 3 for cohorts after you. Yeah, amazing. All right, I think we're a little over time, so let's go to the second question. Amazing. What good things happened in the meeting today?
Yes, I agree, Maxwell.
All right, one more minute, I think, and we'll go to question 3. I agree as well, Oliver. Very cool pictures. Okay, question 3. What should we do differently next time at January 21st meeting?
Mm-hmm.
And I think there's just one more question, right, Wendy? What did you want to happen but didn't happen today?
Mm,
We did run out of time.
Good point.
Yeah.
yeah.
Right.
All right. Yeah. Well, um, we do have email for Dr. Nguyen if you would like to ask questions later on. Yeah.
Thank you, everyone, for taking the time to give us feedback. Have a good night.
Okay, well, have a great
And
holiday
thank you so
season.
much. Oh, go
We'll
ahead.
see y'all in 2026.
Woo. And thank you, Chi, so much. It was a beautiful, beautiful and amazing talk and
Yeah,
really
thank you. And sorry, I should have planned a little bit better. I think I planned an extra 10 minutes.
that's all right. We should have stopped ours a little bit sooner.
Yeah, it was so interesting. That was hard to do.
Yeah.
Okay, all righty. I'm signing off because I have one more Zoom to do tonight.
All right.
Well,
Take care.
Master.
Bye.
Bye.
Thank you.